So homework 2 was out a little later than I thought, but I put it up on Sunday. So it's due as usual next Friday. Okay, so and I would say start early because the homework is not very difficult, but it's a bit lengthy. And please ask if you have clarifications, because this is one of the homeworks where if you understand what you need to do, it's actually not very complicated. You've got to understand what you need to do. Okay, so just ask one thing if you have questions about the homework. Okay, so I've tried to clarify things as much as I can, but clarification. Okay, so that's that, and I wanted to just quickly,
For the homework, do we have the latex version?
Oh, do you want the latex version? Yeah, can you post a comment on this, and I will put up the link. Alright, so the last class, we were looking we continued looking at greedy algorithms. We've been doing that for the last few classes. And what we saw last time was this coverage problem, where we said that the greedy algorithm does not actually find the optimal solution, but it finds something that's close to the optimal. Okay, and this is an example of what are called approximation algorithms. And this is the first example that we saw in this course. Okay, so it's an example of an approximation. And we said that the greedy algorithm always finds a solution that is guaranteed to be at least some 0.63 something times the optimum. So it can be worse, but not much worse than that. That's what we said. Okay, and as always, the thing about greedy algorithms is that the analysis is the tricky part. And so that concluded essentially our discussion about greedy algorithms, although we will encounter them more in this course, later in the course. Okay, so, and then we started talking a little bit about local search. Okay, so local search is another common paradigm, and it's again a very natural idea. Okay, so here instead of building up a solution, you start with some solution, some feasible solution. You always try to improve it. Okay, so that's the idea behind local search. And how you improve it is usually in some local ways. Okay, that's why it's called local search. And we saw an example where we had this matching problem. Right? So we had a matching problem. Just to recall, you've got n gifts and n children. Each child has some happiness value for each gift. And you want to assign, we always assume that these happiness values are bigger than 0. And you want to assign gifts to children so as to maximize the total happiness. So So a local search algorithm for this would start with any feasible solution, okay, and it would try to improve it by swapping gifts. Okay, so what we said is you start with some assignment, and now you look at every pair of children. So let's say child I received the gift P sub I, child J received the gift P sub J. P sub I, P sub J are also some indices. So this is what was said. Try to see if this would have been a better assignment. Okay. And and what he said is you can keep doing this. Okay. This is a local modification to the solution, right? Because the solution consists of an assignment for every child. And this is a local modification because you're just looking at two people and trying to change the assignment for those two. Okay, so in that sense, it's a local improvement. And you want to see if changing this improves the total cost. So it's a natural algorithm. Alright, so how good is this algorithm? Right? So the last time, I thought I would just leave it as an exercise, but then have a homework problem based on this, so I figured I should just do this in detail in class. Okay, so what we said last time is we wrote down these inequalities. Right? So we said, what does it mean to be locally optimal? So you've done this bunch of swaps, and you've come to a state where you cannot improve anymore. Right? So what does that mean? It means that if I take, so it means that the cost of this plus the cost of this is at least as large as the cost that you get after you swap. Right? So that's what it means to be locally optimal. So this is the inequality that we wrote down last time. Because if this were not true, you would have swapped these two assignments. Right? So this is what we said last time. Okay, so any solution that is locally optimal satisfies this condition because otherwise we would have swapped. Again, recall that P1 through Pn is a permutation of So this is Pi just denotes the index of the gift that child I was given. So it's just a permutation of one. Alright, so we have this inequality. Right? So now I want to say that this inequality for every I in j, so this is true for all I in j. This inequality for every I in j implies that the locally optimum solution is at least half of the overall optimum cost you can get. So this again is another example of an approximation algorithm. So you're showing that the local search algorithm ends up with a solution that is at least half the optimal. So in your homework, you will show that this factor half cannot be improved. Okay, so you cannot come up with, let's say, 0.75. So, I mean, a few simple examples show this fact. So that's what we'll see. But first, let's show that it is at least half. Okay. So how do we prove such a thing? Right. So we want to use these inequalities that we have. Right. So how do we go about showing these things? And so we would say, let's consider any optimal. Suppose what you've ended up with, the PIs, are not the optimal solution. So let's just say, consider the optimal solution, and let's call the assignment to be like Q1 through Qn. Okay, so Qis are also permutation, and the optimal solution assigns the gift Q1 to 1. This answer gives the Q2 to 2 and so on. Okay, so this is what I mean by the optimal solution is this. So now I want to connect the value of this solution to the value of the locally optimal solution we found. Right? So how would you do that? So what is the value of the optimal solution? This is some notation. Sorry? No, I know, but in terms of these Q's, what is the... It is sum over what? Yeah, so it is it's essentially H1Q1 plus H2Q2 and so on. So this I will write it as sum over I, Hi, comma Q. This is just, by definition, this is the value of optimal. And the value of the solution we have found is simply value of solution we found is simply sum over I, Hi, Pi. Because we ended up with the assignment P and we assumed that the optimum is P. Right? And we want to show that this is at least half of, that this term is at least half of this. Okay, so how would you show this? Any thoughts? And I want you to think like very, in some sense. These would be simple steps, right? So I have I, and say this is Pi, and somebody else, this is Q sub I. Okay, so we were assigning this while the optimum cost was getting H of IQI. Right? So I want to use the fact that this P was a locally optimal solution. Right? Yeah.
So would you kind of group, because you know with your locally optimal solution that, you know, I guess like in groups of 3 or so I think it is, it will be optimal, so then any sort of,
what do you mean
locally optimal, then any swaps would have to be like across boundaries, so could you do like some sort of...
What do you mean by boundary?
Because if you're swapping gifts, right, then it would have to be some sort of complicated swap, so could you like kind of represent it by grouping the presence?
So yeah, maybe think about it. Yeah, okay. So anybody else? So I guess the question you're going to be asking yourself is, so suppose this edge IQI had a really high value, right? And we somehow did not include this in our solution. What does this mean? Right? So does this make sense? Because that's the only way, like we've got to ask ourselves, can this quantity be way larger than this can? Right? I mean, we want to show that this quantity cannot be more than 2 times this. Right? In other words. Right? So how could it be that this quantity is way larger? Maybe you have some edges where this IQI is significantly more than this IPI. And what does that mean in this case? Right? Because remember, this solution was locally optimal. Right? So can we say that, oh, okay, then some swap could have, yeah.
I think it means if we did swap it to be with IQI, then the thing that previously had IQI is that that new swapping is less than the
Right, so what I guess what you're saying is, look, Qi was assigned to somebody in our solution, right? Because our solution also assigned all gifts to children, right? So our solution assigned Qi to some vertex. Let me call it J. Okay, I'm denoting our solution by these strong lines and the optimal solution by dots. So our solution assigned Qi to somebody, let's call it J. Okay. Now, I could have swapped the gifts of I and J, okay, and I could have received a pretty high value, right? But I'm not. But our solution was locally optimal. Okay. So what we have is that H of I Pi plus H of J with Pj. We don't know what Pj is, right? Pj could have been something totally different. Okay. But what we do know is that the cost of this edge plus the cost of this edge. Oh, sorry. My bad. Okay, so I have assumed that our solution assigned J to Qi, right? That's how I defined J. Okay, so let J be that was assigned to Qi in our solution. Okay, I Pj equals Q. So I'm denoting by Pj the thing that that J is assigned to, and I've assumed that that is Q. So that was how I defined J. Okay. So just to recap in case somebody got confused. So basically, I said we started off with the question: can there be an HIQI that is really large? And then we said, suppose there is, then I look at who got the gift Qi in our locally optimal solution, defining that point as J. And so our inequality from before will say that Hi with Pi and plus Hj with Qi. So this is bigger than or equal to H of I with Qi plus H of J with Q. So yeah, I'll pause a little bit and I'll see if you guys agree with this. Any questions about this? So all I'm doing is I'm starting with some I. Pi was the thing that our solution was the gift that our solution assigned to I. Qi was the gift that the optimum assigned to I. And all I'm saying is, so let's look at who our solution gave Qi to. And we are calling that point J. So in other words, Pj is Qi. Because remember, we are giving each gift to some child, right? So in particular, Qi was given to some child. So this is what you did. Okay? So you could have swapped the gifts of these two children, but you did not end up doing so. And the reason is that this inequality holds. So this is why we have this inequality. Okay, so let's just note that all the happiness values are non-negative. Therefore, this sum is at least H of IQ. Okay, so this is trivial, right? Because this thing is non-negative, therefore I just kept this term. Okay, so is this clear so far? All right. So now let's. So what do we want to show, right? So we want to have some kind of a bound on this quantity. Okay, the sum over I h of I q I. We already have some inequality that kind of looks like what we want, right? So we have something is bigger than or equal to h of I comma qi. So we can be bold. Let's just sum over I on both sides. See what you get. So the right side is exactly the cost of the optimal solution. Okay, so the right side is value of the optimal solution. So what is the left side? Actually, if your left side had only the first term, then what is the value of the optimal? Then what is the sum of the left? Yeah, so then this is exactly the value of our solution, right? So what is this term? Okay, so this term we understand. So what we are asking is, so this I will write it as val of our solution plus sum over I h j comma q sub I. Okay, so this is the sum of all edges of this kind, right? And what do these things add up to? Yeah.
I think it's twice the value of our solution.
So you think this term is twice the value of our solution?
No. I think this is the value of our solution.
Yeah. So why is this equal to value? I mean,
Because qi equals to pj, right? And
Yeah.
I can equals to j. So it is.
so what she's observing is that this is yet another way of doing the same summation as this, right? Because you are essentially, when you do this sum over all I, okay, then you are essentially summing, you are looking at different i's, you are looking at the qi, okay, and you are looking at who our solution assigned that qi to. Okay, so this is essentially, if I had Q1 over here, Q2 over here, Q3 over here, and so on, then all I'm doing is I'm looking at our solution. I'm looking at who Q1 was assigned to, and I have h of that term comma Q1, and I'm just summing all the weights of the edges in our solution. So this is essentially another way of counting the value of our solution. So this one was in some sense doing it from counting the values of the edges by looking at the left, and this is counting the value of the edges by looking at the right. Okay, but this is exactly the same term. Okay, so that's the cool thing. And so this whole thing is exactly 2 times value of R. Okay. So this is the nice trick here. Here we are essentially that by doing this, we are just counting the value of our solution in 2 different ways, one from the left and another from the right. And so you have 2 times value of our solution is bigger than or equal to value of R. Essentially, that our solution is at least half as good as the R. So this is it. Okay, so this is a very simple proof. Do you need more convincing? No? Do you need more convincing? No. Okay. Alright. So this shows what we wanted to show, right? So that any solution that is locally optimum is at least half of the total. So in your homework, you will show that if you had more complicated swaps, where you actually considered instead of just looking at pairs of children and seeing if you can swap gift, you look at like triples of children and see if you can reassign the gifts just between that triple. Then the cost of solution you get will be at least 2/3 the optimum. So it's a little bit better than half. And yeah, so it turns out that you can keep doing this if you consider more intricate swaps where you have like 4 people at a time, then you get 3/4 and so on. Okay, so this is the standard trade-off that you see in local search. If you do a more complicated search, then you end up with a kind of a better solution. Okay, so yeah, this is one very simple example that illustrates. Okay, so that's something you will see. Alright, so continue. So I wanted to now look at another very classic example of local search. Okay, and this is gradient descent. So how many of you have seen gradient descent in some form? Okay, so did your ML class already cover it? Okay. Oh, you've already, yeah. Okay, so who here does not take ML? Okay, this is decent size. Okay, so let me just mention this. Okay, so the general question here is you have a convex function over some convex domain D. Okay, convex domain D. And you want to find the minimum of this convex function. Okay, and what do we mean by convex function? Yeah, actually, what is a convex function? Yeah, so the picture is kind of illustrates it, okay? I see hand signs that show it looks like this, right? So, but what is it formally? Yeah.
Has only one optimum.
Okay, but that need not define a convex function, right? Like a function that that looks like this has one minimum, right? So yeah.
I think back in calculus days, it's the second derivative is defined, and I want to say the derivative is always, or the second derivative is always positive.
Yeah, so for single variate functions, this is the definition that you would have seen in calculus, right? So you would have seen, like if you had f defined from R to R or something, then the function f is convex if f double prime of x is bigger than. So this is good for single variate functions, but if you had functions that are defined over Rn, here where you have n variables, right? So then this is not very clear. There is another definition here involving what is called the Hessian, but let's not get there. So a very simple characterization of convex functions is just you have f of x plus y divided by 2 is bigger than or equal to f of x plus f of y. F is continuous. Okay, so it's just you take the average value f at the average point. It is bigger than or equal to the average of the f values. Okay, so is it bigger? Yeah, let's see from the picture. Okay, so if you take a picture like this, what is the average of the f values? It is so this picture is supposed to show x going here, and this is the f value is the height. So I think I got my equal. So yeah, so you want f at the average point, which is this point, the midpoint. So this is x, this is y. So f at f values within this height. Okay, so this is so this is another very simple definition of convex function. Okay, so people often write it as saying f of some lambda x plus 1 minus lambda y is less than or equal to lambda times f of x minus lambda y for all lambda. If lambda equals half, this is exactly what I wrote there. And there's nothing very special about general lambda. You can use it. Lambda. Right? So this is the definition of convex functions. And so the nice thing about convex functions, as he was mentioning, as somebody mentioned, is that if you take a convex domain D, then the function has a unique minimum. So it's strictly unique only if you have a strict inequality here, but that's the point. So, this right down. There are many properties of convex functions, so I will not go too much into it. My goal here is to just tell you that convex optimization can be viewed as local search. Okay, so that's the point I'd like to make. So there's a lot to say about convex optimization, and there are whole classes devoted to this. Okay, so I'm not going to go too much into detail on this, but this is what you should know. A convex function is a function that satisfies this. And yeah, so another fact is that if f things are called strictly convex, okay, then the minimum of f over a convex domain is unique. And yeah, so there's more you can say, that it's always attained in the interior. Okay, so let's not get that, but at least you can say that this is unique. Yeah.
So I think of it as not the case that just having, I guess, the condition f of x plus y divided by 2, that statement doesn't imply that it's actually completely convex, right? Because the convex definition you gave is more general with the lambda term, or does the
Oh yeah, so this is, if f is continuous, it's easy to show that these two are equivalent.
Oh, okay.
Yeah, so it's one of these exercises that you see in high school chemistry. Right, so if f is continuous, these two are. So, all right. So the fact is that if f satisfies this thing with strict equality, then the minimum over convex domain is unique. Okay, so this is what is true. But more generally, so it turns out that if f is convex, then you can find the minimum by just doing a local search. Okay, so I wanted to illustrate this with just an example of a very simple grid. Okay, so suppose your domain is the grid. Okay, so it's just a two-dimensional plane. Let's draw a grid over it. So strictly speaking, if I just had the integer points, it's not convex. But d is not convex. Let's forget about that. Okay, so how do you find the minimum of f over this grid? So you could say, I will start with some point, and I will look. So you will trace some path in the grid, and you ended up with this point, which has the property that nothing around it is smaller than the f at that point. So I'm just looking at all the neighbors, and I pick an arbitrary neighbor where the f value is smaller. And if there is no such point, I just stop. Okay, and I return value of f. So it turns out that these kind of algorithms are actually, they find the approximate optimum for convex functions. Okay. So this is slightly tricky to prove, but yeah, so it's trickier to prove if you have a discrete thing like a grid. But it's yeah, so I'll write a statement where But first, is this grid algorithm clear? Okay, so it's just start at any point. Look at all neighbors. If one of them has lower f value, move to that. Okay. So yeah, you can make sure that this is a reasonable algorithm, right? So you will never repeat a state. Why is that? The inference. Sorry. Sure, but I mean, as the statement goes, right? Like, so what if it's complex? So I'm just asking, why would you never come back to the same point? Yeah, so you're also, this is why this algorithm is called gradient descent, because your value of f is always strictly dropping. Okay? So you can never come back to the same point. You're always in some sense making some progress. Okay? So that's the idea behind this. So this will terminate eventually, and yeah, so we'll show that it terminates only if it finds a reasonable solution. So this is so a more general algorithm. I won't tell you how to really implement this. We will see in the next slide. But a more general algorithm along the same lines is, suppose you are given f from Rn to Rn. So this is now a multivariable function that takes real value. Okay, so it takes in an n-dimensional point and it outputs a value. Okay, so you've got functions like this. Now all you do is start with any x in the domain. So the algorithm will start with any x in the domain. So you've got some domain D. Start with any x. Now you look in the neighborhood of x, okay, which is just defined as a ball of some radius delta. Okay, so it is a ball of radius delta around x. This is often denoted like this. This is ball around x of radius delta. So you look in this ball, and you see if there is some point where the value of f is strictly small. Okay, if so, go to that point and continue. I haven't told you how you find such a, how you search within this ball. Okay, but let's say you can do that. So this is a generalization of this previous thing. Right? So here you are just doing it within the grid. Okay, now you are just looking at the whole sphere. So and you are taking some point. So the algorithm is just if there exists y in ball of x delta such that f of y less than f of x, then move to y and so conceptually this is a very simple algorithm. I haven't told you how to do it. And the claim is that this will always find and you've got to make sure that you are in the domain. This I haven't said yet, right? But you've got to make sure that and y belongs. So the claim is that this will always find the minimum point. Yeah.
The radius is fixed.
The what?
The radius of each sphere is fixed.
Yeah, so I'm just saying, yeah, so I'm picking some delta and I'm fixing the radius. Yeah. I'll talk about that in a little bit. So yeah. Okay, so in general, what this radius is and so on are not very clear, right? But yeah, but let's say that this is true. Let's say you can do this something like this. So this is what I want to do. Okay, and why is this the minimum value for x? I think this is the interesting thing that you need to understand about convex functions. This is what tells you why a local search procedure is likely to work for minimizing convex functions. Right? So, I mean, intuitively, you want to argue that if I'm at a point x, okay, and I have some point x star, which is the optimum, which is what attains the minimum, then a convex function can't have something like you are flat over here, that you have something here, you come back, and you come to something where you are at a lower value x star. Okay, so in this case, x would not be the optimum, right? Because f of x star is less than, so this, remember, the height is the value of f. So we want to say that something like this can happen. Something like this obviously cannot happen because now if you look in the ball, it's going to be decreasing. But maybe it could be that you have happen for that, okay, where you think you are at some local optimum. Okay, so you think you found optimum solution. Somehow it increases later. It increases and comes back. I want to say that this cannot happen for a convex function. And do you guys see why? I mean, I've only defined convex functions using one characterization, so you've got to use the characterization. So, yeah.
So the point you're at is actually at that point at x, and that would be a local minimum, since convex functions have a unique minimum.
I didn't say they have a unique local minimum, and also I didn't prove that fact, right? So they stated it as a fact, but yeah.
It's your definition of the line segment for the next star.
Yeah, so what he's saying is that by my definition, I'm saying that the value of f has to be completely below the segment that joins this. Okay, so that's the geometric interpretation I gave. So I was saying that for any x and y, if I look at lambda x plus 1 minus lambda times y, so if I'm somewhere over here, then this point is less than the line segment that joins f of x and f of y. Okay. And so what this means is that the value of f at some point in this ball, that is maybe this point, this has to be less. So let's just write it. So let me call this point y, where y equals lambda x plus 1 minus lambda times x star. Okay, so this is some point in this ball of radius delta, and it is along x star. Okay. So this was x, and this was x star, and so I'm taking some point y that is in the ball, and it's on the line segment joining x and x star. Okay. And what he said is essentially that we know that that f of y is less than or equal to lambda f of x plus 1 minus lambda f of x star. And lambda is strictly more than 0. We know that, and if you assume that f of x star is strictly less than f of x, so if f of x star is strictly less than f of x, then f of y is strictly less than f of x. Because, if you plug that in, you'll just, if you plug this inequality here, you'll get that f of y is strictly less than 1 minus lambda plus lambda. It's just 1 times f. So, and this is a contradiction because if f of y was strictly less than f of x, you would have moved to that point. So that's that.
I have a question.
Yeah.
So this means that if y is strictly less than fx,
Yeah.
then we will definitely can move from x to x as rate, then the optimal solution.
No. So this is a proof by contradiction, right? So I'm saying, I want to claim that this local search procedure always finds the minimum value for m. What I'm saying is, suppose it does not find an optimum. Suppose local search ends at x, and x star was the true minimum of the function. Okay. Then I'm looking at x and x star, and I'm showing to you a point in the ball around x, radius delta, that has a value strictly less than f of x. Okay, and I'm constructing that point by just moving in the direction from x to x star, okay. And I will move so that I hit this, so that I'm still in this ball of radius delta. So what is the local search procedure doing? Right? So it is around every point, it is looking at a ball of radius delta. Okay. All I'm saying is, suppose x star was out here. So if x star was in the ball, then there is nothing to prove, right? Because I'm already looking inside the ball and trying to see if there's a point that is better. So you can assume that x star was outside this ball. And what I'm saying is that if I look at this line segment, and if I look at this point, which I'm calling y, f of this y is also strictly smaller than f of x. And this is a contradiction because now my local search algorithm would have actually moved to y. It would not have stopped at x. Okay, because as long as there exists a point in the ball that has value strictly less than x, f of x, you are moving to that point. Yeah.
That means that cannot be the graph of f.
Yeah, exactly. So that cannot be the graph of f, and so you can't have an f which increases like this and comes back to something lower, because the graph has to be less than this line segment. It has to be completely below this line segment, and which means that at this point y, it should have been below f of x. That's another question. So, so think about this a little bit. I'll just pause, see if you have any questions. Okay, but this is the reason gradient descent works, okay, for convex one. Because you can't have an optimum that's like way out and have a value of f that is strictly small. Yeah. Sorry?
Shouldn't the claim dissolve the approach to rather than just refine?
Oh, so the this is not very clear, I guess. So it's like the final or like the locally optimal point will be the will always be the minimum. That's what I mean. So if you ended up with this with an x, which is the locally optimal, that will be the minimum.
I have
That's
a
it.
question.
Yeah.
Means you choose, if you say that if you cannot find the optimal, means the algorithm cannot find optimal, and it will stop at some point. So how can you say that it cannot find, maybe it's run forever? It won't
So
stop.
I've already told you that it will not run forever, right? Because the f value strictly drops.
Strictly wrong, but maybe it's still run forever.
Right. So you're talking about convergence issues.
Yeah.
Right, so this I have swept under the rug. You have to, in principle, you have to take into account convergence issues. You will stop when you are below some accuracy threshold. Okay, so a couple of slides later I will talk about it. Okay, but yeah, so you stop when you are happy with how far you are from the optimum. Okay, so because this is a continuous optimization. So what they are saying is, the value of f will drop, but maybe it will keep converging. It's like maybe the value of f after iteration n is like 1 by n, right? So it will keep dropping to 0, but it won't really ever converge. Okay, but you always have some accuracy you have in mind, and you stop when you hit that accuracy. Okay, so that's something that I'm.
But in kind of mathematical point of view, I think that because we have fixed the radius, so maybe we can prove that for it within the radius, this drop means the value drop has a minimum value of because it's a compressment.
Right. So this is all about how you show convergence, and that's the kind of the right idea. So you have to assume strict convexity and so on. Okay. So yeah. So he's trying to patch this by giving explicit bounds on how fast this will converge. Okay. So it turns out there are well-known ways of doing this, and you will see this in your machine learning classes. Okay. So yeah. My point here was just to illustrate that you had a convex function. The convexity property, which is essentially this equation that we wrote here, this implies that a local optimum is a global optimum. That was my point. Yeah.
And so, clarifying the proof, it only relies on f of y being better than f of x. It doesn't rely on y being optimal inside of the ball, right? Like it doesn't,
Yeah.
y doesn't have to be
Y
less
need
inside
not
of
have to be optimal. Yeah. Okay, so so there could have been that just had values strictly less than f of x, but it was not the minimum in the ball, and that would still work for this. Yeah. Okay, so this is so this is just what I wanted to face. As you pointed out, there are a lot of questions to consider. Right. So firstly, I haven't told you how you do this optimization, right? How you find a y in this ball so that f of y is less than f of x. So it turns out this step is actually easy. So this is the reason this is called gradient descent. So you move along the negative direction of what's called the gradient of f. Okay. So if you know this, it's great. Otherwise, don't worry about it. So it turns out this is an easy step. Okay, so just move direction opposite to the gradient. And so there's also other things like how many steps do we take? This is the point that you're saying. Because I essentially defined it as you keep going until you actually never find a point that has strictly smaller value. Okay. So as I defined it, it can take forever, but there are ways to get around this. And the question is also what is the step size? I've always assumed that you look in a delta radius ball, right? Should there always be a fixed delta? That's something that you had asked. Okay, so so should this be fixed or should this vary as you go along? Right. So these are all so there are entire courses on gradient descent. So I don't want to go into too much detail on this. So these are all interesting questions. And how you do this actually determines how quickly you converge. So these are not trivial questions. Okay, so these are they're actually very interesting things, but you will see them in optimization courses. It turns out that if you play with the step size really carefully, you can just dramatically change the convergence rate. There are all these very interesting properties. Okay, but we don't have time for that. Okay, but alright. But the point to remember is that gradient descent is one example of a local search algorithm where you will always find the global optimum. Okay, and the convexity of the function implies that what you found is the global optimum. Alright, so this is like a quick summary of gradient descent. Like you always, of local search. You start with some solution, you move to some neighboring solution. And how you pick these neighbors often determines the complexity. And yeah, as we noted, this is not always optimal. So I don't know if you noted, but you will prove in your homework. That is not always optimal. Okay. And as I mentioned before, the number of steps can be large if it's not done carefully. Okay. So this again I wanted to put in the homework, but already it was too big, so I did not put it. But there are examples even in this matching case where if you don't do these swaps carefully, you can just keep swapping for a really, really long time. Okay. And so there's a standard trick for this, which is you find the swap that maximizes the objective, okay, at every step. Or you say that you swap only if you can ensure that you've made enough progress in your objective value. Okay, so this will automatically give you a bound on how many steps you can do. So these are standard tricks to make sure you always improve by a significant amount. So this is to make sure that you don't take too many steps. Alright, so this is a quick little summary of local search. Any comments, thoughts? Yeah?
Would adaptive step size also be an appropriate approach? If the swap doesn't achieve a certain level, then you increase your step size?
Yeah, but in this case, what is the step size, right? That's the question. So you have to look at 3 people or something like this, you're saying. Yeah, you could do that, but then it still becomes more complicated to check 3 things. Yeah, so yeah, you could do that. You could only you probably don't want to start off by checking triples. Maybe you just check pairs to start with, and maybe after you've converged, you check for triples and so on. That could actually eventually be faster. Yeah, but I don't know if it's significantly fast. Yeah, that's a good point. Alright, so yeah, so the other thing to which I forgot to mention about gradient descent is that it's an algorithm that people use a lot. People use it also for non-convex functions. Like the whole theory of neural networks, you just optimize non-convex functions using gradient descent and you hope for the best. So this is very common. And often you end up with pretty decent solutions. Okay, so even if the function is not convex, because presumably the local minima are not too bad compared to global. Okay, so that's one comment that I want to say. It's probably the most used algorithm in machine learning. Right, so. Okay, and all the tricks people come up with for convex functions, people use them for non-convex functions as well, without really worrying too much about it. Because you always end up with something, right? So that's the nice thing about these local search type methods. You always end up with some solution. It need not be great, but it's reasonable by some standard. Right? So Okay, so let's switch gears now, and then the rest of today and maybe next time we'll do some very basic things about graph algorithms. Yeah, and then we'll move on to something else. So I wanted to cover some basic things that all of you should know. Hopefully, many of you have seen these problems. Okay, so all right, so let's start with some basics, and we'll be talking about shortest paths and graphs, and we'll be doing things at somewhat highish level, okay, because this is again very standard material. So, all right, so let's go into that. That being said, one interesting thing about shortest paths is that it's one of the first polynomial time algorithms people have thought about. Okay? So actually, what is the problem? It is basically you're given a graph. Let's think of a directed graph. Think of a road network if you are, if you want a concrete example. So you have vertices, which are, let's say, places, and you have edges, which are essentially the lengths of the edges connecting, length of the path that connects you to B. So you have some weighted graph, and possibly directed. Let's assume that graphs are directed for now. Okay, so there's probably a different length for going from U to B than for going from B to U. There's a length U to B. Okay, so this is the definition of the problem. And you're given two vertices U and B. They need not be directly connected. And you want to find the length of the shortest path from U to B. So you're given some with some edges and some lengths. Okay, something like this. Okay, so you're given so you have a bunch of vertices and you have directed edges, and the weight of that edge tells you the length of the path, the distance between you and B. So this is the shortest path problem, and your question, and the problem is what is the length of the shortest path between two given vertices U and B? And as I was saying, this is one of the first problems that people have thought about, first computation problems that people have thought about. Because initially, so this was in the 1950s, and until that point, people thought that these kind of problems are trivial because there are only finitely many paths between any two vertices. Check them all, there is some minimum, and you can find the minimum. Right? But of course, this is totally infeasible even if you have reasonable sized networks. Okay, so that's the reason I guess Dijkstra came up with a much faster procedure to do it. And if you read his paper, it's very funnily written. I mean, he talks about why. I guess it is still interesting. He talks about why it's so infeasible to explore all paths. So, yeah, but at that time they had to argue like that. So, yeah.
So we're adding up the weights and now counting the number of edges.
Yes. Okay, so the length of the path is defined by the sum of the edge weights. Okay, so when I say the length of the shortest path, the length of a path okay, so for instance, in this example, right, if I took, let's make this 2. Okay, so if I took the path from U to W, and W to B, it would be a path of length 7. Okay. But if I took the seemingly longer path of going all the way here, it would be a path of length 6. Okay. So yeah, so the question asks to find the length of the shortest path, and this is why the problem becomes a little bit non-trivial. Okay. So yeah, so if the graph is not weighted, then what you're saying is right. So if the graph has all edge weights being equal to 1, then you just want the path with the shortest number of hops. That is a much easier problem. Why is that?
No,
Yeah.
just trying to figure out.
Yeah. Okay, but but let's say I told you that the graph just has all edges of weight 1. Okay. Now, how would you solve this problem?
Just do a
Depth
depth search and
first search. Okay. So yeah, so the suggestion is that you do a depth first search. Would that be the reason why? Yeah, so I guess a depth first search would essentially explore the. So both breadth first and depth first search are just ways of exploring the graph, right? So you start with some vertex u and you explore the full graph. Depth first essentially tries to do goes to a vertex, explores that, and comes back and so on, right? But depth first search, if you think about it, does not necessarily find the shortest path. You just explore the graph in some order. Breadth first tries to explore all the immediate neighbors first, then it explores all the neighbors of neighbors, and so on. So that actually finds the shortest path because you're going level by level in the graph. Okay. So if the graph is not weighted, breadth first search, which I don't know if you have seen the breadth first search, but hopefully all of you have seen. If not, you should definitely be familiar with these things. So go back and read. Okay, so breadth first search finds the shortest path. Because so this essentially works by starting with a U, exploring all the neighbors. You mark them as visited. Then you go through these neighbors one by one, and then you explore these guys, and then you explore these guys, and so on. Okay, so you go level by level, which is why you will automatically find the shortest path. Okay, so this is if you have unweighted. Okay, so now what if you had weighted edges? Right, so the question he asked is that the length of the shortest path here need not use the fewest number of edges. Right, so that is what this example also shows. Yeah. Sorry.
The edges are weighted, so there's a value approach is kind of modification of the system. 5 because let's say the edge length is 3.
Yeah.
And then basically you are adding 3 variables.
Yeah.
You say the variables kind of
So what he's saying is, I can always reduce to the case of unweighted edges by saying if I had an edge of weight 3, you replace it with a bunch of nodes. Okay, so you add 2 nodes to this path, and now you pretend that these are weight 1. So this would be exactly the same as having an edge of weight 3. Right? So this is a correct procedure, right? Clearly, but this is not very preferable. Why is that? Yeah. Yeah, so if you have huge weights, right? If you had a weight of 1 billion, then you would end up adding 1 billion vertices where your original graph could have had 10 vertices. Okay, and this seems rather inefficient. Yeah.
Well, but it seems like it can be arbitrarily bad because, like, and not even it'd be impossible to find a solution if edge weights are allowed to be real numbers.
Yeah, so if you had edge weights of I don't know, pi or something, then it would be hard to implement something like this. Right? So that's the other thing. Right? So yeah, so this goes back to this discussion we had about weakly and strongly polynomial. And there's also some post comment that I made on Canvas. Okay, so it actually turns out to be related to that. Okay, so let's not step further into the domain, but this is an interesting point to know. Okay, that you can, if all the edge weights are kind of small, then you can actually just replace an edge with multiple copies. So this used to be one of my final exam problems. Alright, so that's this. Okay. Alright, so now, yeah, so suppose we don't do this, right? So you just have weighted edges. How do we now try to get over this issue? So can you think of iterative algorithms that kind of get over the issue like this? So I wanted to give a hint. Okay, so does the hint make sense? So how would you?
So we could like keep track of the distance covered till now and maintain a minimum on each node. Like what is the minimum distance that we had to take to reach this node? And on the destination we have the minimum from source to the destination. That also will be evaluated.
But how do you? I mean, so how do you maintain these things?
So maybe have some sort of iterative procedure where you go and maybe you find some, like use breadth first search or something initially to find the shortest path between like all of the different nodes, and then you can kind of use that information to know kind of build up a solution that way by keeping track of not just one shortest path to your thing, but all of them, so that way you know, oh, like between nodes D and E, even though it might not appear like that, like it looks like it's some really expensive cost to get there because that's the immediate edge. I know that there's this faster way to get there. You could kind of use something like that. That's how vectors work, right?
Yeah, so vaguely this is what you would like to do, right? So what is trying to say is, I think both the answers are trying to say that from you, keep track of distances. So let's say first you do some breadth first search. Breadth first search, remember, only picks the least number of hops. Okay. So to avoid confusion with shortest paths, I will use the term number of hops, which is the number of edges you use. Okay. So you can use breadth first search, and you can compute some tentative values for the distances. Okay. So you maintain, the main idea is for all v in the graph, maintain distance of v. Okay. And this you define it using this initialized using breadth first. So note that this need not be the true distance, right? Like for this, if you had this graph, this vertex v would have been assigned 7 because it's there's a length 2 path that would have given 7. So you would have found this, and whereas the true shortest path has length 6 and that was a much longer path. Okay. So yeah, so you just initialize some way, okay, and initialize between BFS. Turns out you don't even need to do this. You can just initialize everything to infinity and except the vertex u, and that also works. Okay, but assume you initialize using BFS. Okay, it's a reasonable place to start. And now, what you can do is you can see if there are possible shortcuts, right? Like you can now try to see. So for an edge, let me call this ij. Okay, so if you had an edge ij like this, you try see if this of j is strictly bigger than this of I plus this weight of the length of I. Okay. So you could say, suppose you initialize using BFS. Okay. Now you try to see if there are some I and j that have an edge for which this property holds. Okay. And if so, you know that distance j is wrong, right? Because you know for sure that there is a shorter path. Okay, so then we know this j originally computed is interesting. Okay, and the true distance is at most distance of I plus Lij, right? Because you could have gone to I, which from U to I, which had a length of at most distance of I, and you could have taken this path Li, because there was an edge from I to j. So actually, yeah, I see many people, I guess, with possible questions. So maybe I will explain what is going on, right? So what am I doing here? I'm just initializing all these distance values using BFS. These are not the true distance values from U to V. These are not the lengths of the shortest paths. But all I know is that there is some path from U to any vertex V or any vertex I whose cost is at most distance of I. Okay, because I've initialized using BFS, so I know that these are overestimates for the shortest path, right? Because there is some path that has this cost, and in particular the BFS path has this cost. But these need not be the length of the shortest paths. And for some vertices, maybe these are the shortest path, but we don't know for which vertices are. Okay, and in some sense, we're trying to correct these values. Okay, so that's the idea behind this algorithm that I'm now proposing. Okay, so I'm just saying start with some values and we try to update them like this. Okay, so I'll just say if there is some edge ij for which this is true, then I'll update the distance value for j to be equal to this, j equal to this. And we'll see next class that if you just keep doing this, just see if there exists an edge such that this condition holds, and you update it like this. And you just repeatedly perform this operation. You'll always get, this procedure will converge to the right shortest path distance. Okay, so that's what we'll show next class. And